Okay, so welcome to the afternoon session of today's talks. So our first talk of the afternoon is given by Sheila Sandon, and the title is Non-Squeezing and Some Other Global Rigidity Results on Locally Conformal Symplectic Manifolds.
Thanks a lot. Thanks a lot for the invitation. I had missed the last few editions, so I'm really happy to be here this time. So let me start with a short introduction to LCS manifolds. So a locally conformal symplectic form on a manifold M is a non-degenerate 2 form that locally can be written as a symplectic form multiplied by a positive function. So there exists an open cover Ui of M such that omega restricted to Ui is equal to a positive function times some symplectic form. And since omega is a non-degenerate 2 form, the dimension of M is necessarily even. And if the dimension is 2, then omega is necessarily closed, so a symplectic form. So from now on, we will always assume that the dimension is at least 4. Then in that case, omega is not necessarily a symplectic form, not even locally, because the differential of omega restricted to Ui is equal to e to the mu I differential of mu I wedge omega I, which is equal to d mu I wedge omega restricted to Ui, which is in general not 0 unless the function nu I is constant. And another observation is that these local 1 forms, d mu I, they glue to a well-defined 1 form on the manifold M. Because on each intersection, we have that E mu I omega I is equal to E mu J omega J. So 0 is equal to the differential of omega I, which is equal to the differential of E to the mu J minus mu I omega J, which is equal to the E mu J minus mu I differential of mu J minus mu I wedge omega I. And since omega I is non-degenerate, vanishing of this wedge product implies that this 1 form has to vanish. And so the differential of mu I is equal to the differential of mu J. And so we get a well-defined 1 form eta on M such that eta restricted to Ui is equal to d mu I. Now the form eta is closed because it is locally exact. And this relation here implies that the differential of omega minus eta wedge omega is equal to 0. And this expression is also written as d eta omega is the twisted differential of omega by the 1 form eta. So this d eta is called the Lichtenrovich the Raman differential. And it is really a differential in the sense that d eta wedge d eta is equal, composed with d eta is equal to 0. Okay, so we have seen that given an LCS form on omega on a manifold M, there exists a 1 form eta such that omega is eta closed. Conversely, if omega is a non-degenerate two-form such that the eta omega is equal to 0 for some closed one-form eta, then omega is LCS. Because there exists an open cover UI such that omega eta restricted to UI is exact. And then we can set omega I to be e to the minus mu I omega restricted to UI. And then this expression here, this equation, implies that omega I is symplectic by a calculation similar to the one we had done before. So an LCS form can be equivalently defined as a non-degenerate two form that is eta closed for some closed one form eta. And this closed one form eta is in fact uniquely determined by omega and is called the Lie form. Of omega. And now LCS manifold is a manifold M with an equivalence class of LCS forms under the equivalence relation for which omega is equivalent to e to the f omega for any function f. And such an equivalence class of LCS form is called an LCS structure. Now, if eta is the Lie form of omega, then the Lie form of e to the f omega is eta plus the f. So an LCS manifold can also be denoted by the manifold M with an equivalence class of pairs eta omega under the equivalence relation for which eta omega is equivalent to eta plus the f e to the f omega. So the notation is a bit redundant because, as I said, eta is determined by omega, but it is somehow useful to keep a track of the Lie form in the notation. So a first example of an LCS manifold is given by symplectic manifolds. More precisely, conformal symplectic manifolds. Now, a conformal symplectic manifold is a manifold M with an equivalence class of symplectic forms under the equivalence relation for which omega is equivalent to EC omega for some constant C. So here we multiply by a constant and not by a function because if omega and e to the f omega are both symplectic, then f is necessarily constant. Because 0 is equal to the differential of e to the f omega, which is equal to e to the f df wedge omega, and since omega is non-degenerate, this implies that the f is 0. So this is very much the same calculation that we did before on LCS manifolds. So recall that for LCS manifolds, we have seen that on each intersection omega I intersected with omega j, we have that e to the mu I omega I is equal to the e mu j omega j, and the fact that omega I and omega j are symplectic implies that nu j minus nu I is constant. So we have that omega I is equal to EC omega j. So we can describe an LCS manifold also as a manifold that locally has the structure of a conformal symplectic manifold. And if the Lie form is globally exact, then the LCS manifold is globally a conformal symplectic manifold. So if M eta omega is an LCS manifold with the Lie form exact, then eta omega is equivalent to 0 e to the minus eta omega, and this is a symplectic form. And the conformal class of this symplectic form is uniquely determined by the LCS structure, so we can identify this LCS manifold with the conformal symplectic manifold e to the minus mu omega. Okay. So an important remark is that, in fact, any LCS manifold is covered by a conformal symplectic manifold. Indeed, we can consider the cover defined by the kernel of the homomorphism defined by the class eta on the fundamental group of M, which is defined just by integrating eta along a loop. And so, in other words, we can write M as the quotient of the fundamental group by the equivalency relation for which gamma 1 is equivalent to gamma 2 if the integral of eta along gamma 1 is equal to the integral of eta along gamma 2. And if we pull back the Lie form, eta, so here this manifold is, then this is exact. Primitive is given by the function given by integrating eta along a path. And so the pullback of eta and the pullback of omega is an LCS structure on M bar, which is, as in the previous example, the Lie form is exact. And so M bar has the structure of a conformal symplectic manifold. It is called the symplectic cover of the LCS manifold. Okay, so first example of LCS manifolds is conformal symplectic manifolds. Second important example is given by the locally conformal symplectization of contact manifolds. So given a contact manifold YXC with contact form alpha, the locally conformal symplectization is the manifold S1 cross Y with the LCS structure defined by minus d theta d minus d theta alpha, where theta is the coordinate on S1. And the symplectic cover is the usual symplectization, or better, the conformal class of the usual symplectization. Indeed, by the previous example, the symplectic form here is e to the theta d minus d theta alpha, but an easy calculation shows that this is equal to that. Okay. And a third important example is given by twisted cotangent bundles. So given beta, a closed one form on a manifold B, we can undo the cotangent bundle of B by the LCS form, LCS structure defined by the pullback of beta and the twisted differential by the pullback of beta of the standard Liouville form. So here beta, pi is the projection, and lambda is the standard tautological one form. So this is denoted by T star beta of B, and it's called the twisted or beta twisted cotangent bundle of B. And it should not be confused with a cotangent bundle with a magnetic symplectic form, as was described in the talk of Gabriele. Those are sometimes also called the twisted cotangent bundles, but it's something different than this. Okay, so LCS manifolds, they have been first studies in the 40s and 50s by Lee and Lieberman, and then in the 70s and 80s by Weismann and Lichtenreuovich, and then by several other authors, and more recently by Eliashberg-Murphy, Bertelson-Munez, Chantren-Murphy, Chantren-Sackel, and Courier, O. Savelyev, and other people. And it turns out that all the basic notions of symplectic geometry, they easily generalize to the LCS case. For example, we can define the Lagrangian submanifolds and Hamiltonian isotopies. So a Lagrangian submanifold will be a submanifold half-dimensional such that omega on L is 0, where omega is a sum, hence any LCS form representing the LCS structure. And an Hamiltonian isotopy is defined by the equation omega xt is equal to d eta ht. So more precisely, we say that the vector field xt is a Hamiltonian if for some, hence any pair eta omega representing the LCS structure, the one form omega x is eta exact. And then ht is called the Hamiltonian function with respect to the representative eta and omega. So equivalently, we can say that xt is Hamiltonian if on each ui, xt is Hamiltonian in the usual sense with respect to the symplectic form omega I. So here, the vector field xt defining the Hamiltonian flow is defined globally. The only difference with respect to usual Hamiltonian dynamics is that here the symplectic form and the Hamiltonian function are defined only locally. So we can say that LCS geometry is a generalization of symplectic geometry that allows to study Hamiltonian dynamics in a more general context and on many more spaces than symplectic manifolds. Yeah.
Is it right that there is a local coefficient system somewhere in the background? And I should think of differential forms just taking values in this local coefficient system.
Yeah, I think in the work of Chantren and Murphy, it appears, but it doesn't appear in our work. We just work with usual singular homology, as I will say.
Yeah, but the symplectic form truly closed.
On a line bundle, on the total space. Yeah, sure. Yeah. That's still, again, one more equivalent definition. Yeah, I'm not going to use that point of view in the talk. But that's also useful. So LCS geometry has the same local flexibility properties as symplectic and contact geometry, in particular Darboux theorem, Weinstein theorem, and so on. So the question we are interested in is whether there exists some global rigidity phenomena. And as far as I know, so the only global rigidity result in the literature that I have seen, and it is similar in spirit to the results that we are used to in symplectic geometry, is the theorem of Chantraine and Murphy. Of 2016 that says the following. So we consider L a Lagrangian manifold in a twisted cotangent bundle. We assume that B is compact. And we assume that L is Hamiltonian isotopic to the zero section, and also that it intersects the zero section transversally. Then the result is that the number of intersections is at least equal to the rank of the Novikov homology of B with respect to the class of beta. So this does not imply that we always have intersections, because the Novikov homology can be zero. So if beta has no zeros, then the Novikov homology is zero. And in that case, in fact, it's very easy to see that the zero section can be displaced. It is just displaced by the so-called Lie flow, which is an analog, an LCS analog of the Reb flow. It's the Hamiltonian isotopy generated by the Hamiltonian function, which is constantly equal to 1. And it's very easy to see that if beta has no zeros, then this isotopy displaces the zero section. But if the Novikov homology is different than zero, then we have this multiplicity result. So now let me write a list of our results. So the first result is in the same context of the theorem of Chantraine and Murphy. But we don't look at intersections with the zero section, but at Lie chords. And we show that such Lie chords always exist. So from L to the zero section, under the same hypothesis than the theorem of Chantraine-Murphy, B is compact and L is Hamiltonian isotopic to the zero section. So as I said, and as I will say again more precisely later, this Lie flow is an analog of the Reb flow. So these results can be thought of as an analog of the result of Chekhanov and Chaperon about the existence of Reb chords for Legendrians in the one-jet bundle that are isotopic to the zero section. And in fact, it turns out it's a very easy consequence of that theorem. And the second result, so we introduced the notion of translated points for LCS diffeomorphisms. And we show that those points always exist in the at least in the C0 small case. So existence of translated points of Hamiltonian LCS diffeomorphisms of C0 small Hamiltonian LCS diffeomorphism on a compact LCS manifold. And then we have a series of results on the conformal symplectization of R2n plus 1 and the conformal symplectization of R2n cross S1. So here we show that there exists a bi-invariant partial order. So this is analog to the result of Viterbo 92 on the Hamiltonian group of R2n. So it's a bi-invariant partial order on the group of compactly supported Hamiltonian diffeomorphism of this manifold. It's an analog of Viterbo and of Bhupal 2001, the partial order defined in the contactomorphism group of R2n plus 1. And then here we also defined a bi-invariant partial order, but also an integer valued bi-invariant metric on the Hamiltonian group, and an SES capacity for domains that allows to prove a non-squeezing SES non-squeezing theorem. And so this is analog to, again, Viterbo in the symplectic case on the Hamiltonian group of R2n, and of my work of 2010 and 2011 on R2n cross S1, and also of Eli Ashberg, Kim, and Polterovich 2006 for the non-squeezing theorem. Although we will follow the proof that I gave using generating functions and not the original proof of Eli Ashberg, Kim, and Polterovich. So let me just state the SCS non-squeezing result that we prove. The theorem is that if pi r2 squared is smaller or equal than k is smaller or equal than pi r1 squared for some k integer, then there is no compactly supported SES Hamiltonian symplectomorphism of S1 cross R2n cross S1 that sends the closure of S1 times ball of radius R1 times S1 inside the second domain, ball of radius R2 cross S1. Here, instead, if we start with the ball of capacity smaller than 1, then we know that squeezing exists, because by another theorem of Eli Ashberg, Kim, and Polterovich, we know that contact squeezing already exists on the corresponding domains in R2n cross S1. So whenever we have a contact isotopy in a contact manifold, we can always lift it to an Hamiltonian isotopy of the LCS symplectization. And so it remains the case where both capacities are bigger than 1 but are not separated by an integer. There, in the contact case, we know we cannot squeeze. And last year, with Maya Fraser and Bingyu Zhang, I gave a proof of that using a ZK equivariant generating function homology theory. And we expect it should be possible to generalize that proof as well, but we didn't do it yet. So for the moment, we just have this first result for integers. So in the rest of the time, I'm going to comment more on these results. Yeah.
Is the second point here the consequence of the first point?
Yeah, sure. And the Weinstein theorem. Yeah. Okay, so the main tool we use is generating functions. So it turns out that the theory of generating function extends very well to the LCS case, in contrast to fluoromology and holomorphic curves that seems quite hard to generalize. So let me first explain the baby case of a generating function in the LCS case. So if we just have a function defined on a manifold B, then the twisted differential of f, seen as a map from B to the twisted cotangent model of B, is a Lagrangian submanifold. So the twisted differential is the map that sends Q to the usual differential of f at Q minus f of Q beta q. And this is Lagrangian because recall the LCS structure here is defined by the S form given by the twisted differential of the standard Liouville form. And by the tautological property of lambda, we know that the pullback of lambda by d beta f is d beta f. So the pullback of omega will be d beta of d beta f, which is going to be 0. So this is the LCS analog of the fact that in the symplectic case, so now we say that f is a generating function of this Lagrangian. This is analog to the fact that f is a generating function of the differential of f, seen as a Lagrangian in the usual cotangent bundle. And it is also, in the contact case, a generating function for the one jet of f, as seen as a Legendrian in the one jet of B. And similarly to the symplectic and contact case, one can generalize this observation to the case of a function that is defined more generally, let's say, on the trivial vector bundle over B. In the usual theory, we do the following. So we assume that the differential of f is transverse to the fiber conormal bundle of this vector bundle. And then we look at the set of fiber critical points. Then this space is a submanifold of beta times R to n of the same dimension of B. And then we look at the map from this set of fiber critical points of f to the cotangent bundle of B, defined by sending a fiber critical point E to the covector based at the projection of E to B, and is defined as follows. Applied to a vector x is equal to the differential of f at the point E applied to any vector x hat that projects to x. So this is well defined, does not depend on the choice of x hat because E is a fiber critical point, so the differential of f vanishes at vertical vectors. Okay. Now in the twisted theory, and this is, can be seen easily to be a Lagrangian submanifold, and in the twisted theory, we do the same, but here we take the twisted differential instead of the usual differential. So we consider a map EF beta from sigma f to the twisted cotangent bundle of B. Now this is defined by saying that EF beta E applied to a vector x is equal to the twisted differential of f at E applied to any vector projecting to x. And this can be seen to be Lagrangian by the same reason, essentially, as here in the baby case. And now, similarly to the symplectic and contact case, we have an existence and the uniqueness results of generating functions quadratic at infinity for Lagrangian submanifolds Hamiltonian isotopic to the zero section. So this is a theorem due to Chantraine and Murphy. It says the following: if B is compact, then any Lagrangian submanifold of a twisted cotangent bundle of B that is Hamiltonian isotopic to the zero section has a generating function quadratic at infinity, which is essentially unique. So here, sorry, I forgot to say, we say that f, in this case, f is a generating function. So if this map is an embedding, we say that f is a generating function of the image of this embedding. Seen as a Lagrangian in the twisted cotangent bundle. And so this theorem is analog to the theorem that we have in the symplectic case That was proved by Lado and Mackenzie-Korab, and in contact case by Chaperon and Chekhanov concerning existence of generating function for Lagrangians and Legendrians, and Viterbo-Teré for the uniqueness part. And in fact, it turns out that in the SES case, we get this theorem also almost for free. It turns out to be an easy consequence of the corresponding result in the contact case. Essentially because this Lagrangian here, since it is Hamiltonian isotopic to the zero section, it is exact in some LCS sense. So it can be lifted to the contactization of this LCS manifold, which turns out to be the twisted one jet of B. And then there is a strict contactomorphism from the twisted one jet of B to the usual one jet of B. And so if you take the image of the lift of L by this strict contactomorphism, you get a Legendrian in the usual one jet. And a function f is a generating function of that Legendrian if and only if it is a generating function of our initial Lagrangian. So we can deduce this theorem from the theorems, corresponding theorems in the case of Legendrians. So now, given a Lagrangian Hamiltonian isotopy to the zero section, now we know that we have a generating function, quadratic at infinity. Since this function is quadratic at infinity, it has critical points. So the question now is to see these critical points, they correspond to what for the given Lagrangian. And in fact, Chantrain and Murphy, they did not look at usual critical points of the generating function. They looked at twisted critical points, which are the zeros of the twisted differential of f. And those twisted critical points, they correspond to intersections of the Lagrangian with the zero section, but they don't always exist. They are governed by Novikov homology that might be zero. So instead, we look at the usual critical points, and those, they always exist, and it's not difficult to realize that those critical points, they correspond to Lie chords from the Lagrangian to the zero section. So this is what I'm going to discuss now. So let me first define more precisely the Lie flow. So we have an LCS manifold, M eta omega. Now the Lie vector field with respect to a representative eta omega is the vector field R omega defined by the relation omega R omega is equal to eta, and the flow is called the Lie flow. Equivalent, we can say that the Lie flow is, in other words, is the Hamiltonian isotopy with Hamiltonian function constantly equal to 1. Because recall the equation defining an Hamiltonian isotopy is the eta ht. In fact, I should take the convention with the minus, and then the twisted differential of the function 1 is equal to, so minus the twisted differential of 1 is equal to eta. Okay, it's the differential of 1, which is 0. Okay, and now, first example, the Lie flow of a symplectic form is the identity. More precisely, if we have an LCS manifold with Lie form exact, then we have seen that eta omega is equivalent to 0 e to the minus mu omega, and this is symplectic. And the Lie flow of 0 e minus mu omega is the identity. Right, because the Lie form is 0, and omega is non-degenerate. And by the way, more generally, the Lie flow of another representative, eta omega, this is the Hamiltonian flow in the usual sense with respect to the symplectic form E minus mu omega of the autonomous Hamiltonian E minus mu. Second example is on contact manifolds. So we have a contact manifold with contact form alpha, and the Lie vector field on the locally conformal symplectization with respect to the standard representative minus d theta d minus d theta alpha is 0 in the S1 component and the Lie vector field in the contact manifold component. So this is the Lie vector field of alpha. So in this sense, we can say that the Lie flow is a generalization of the Lie flow to LCS geometry. And, but there is a big difference with respect to the Lie flow, is that in general, the Lie vector field could vanish. So for symplectic forms, is a case where the Lie vector field always vanishes. On locally conformal symplectization is the case where it never vanishes, but then we have a lot of intermediate cases. And one of these intermediate cases is the third example, the Lie flow on a twisted cotangent bundle with respect to the standard representative. Is the flow defined, so it sends a covector sigma q to sigma q plus t beta q. So we move along the fibers and in direction of beta. Okay, so here if beta is 0 at q, we will not move at all. So the Lie vector field will be 0. So now we have the following proposition. If f is a generating function of a Lagrangian L of a twisted cotangent bundle, then there is an injective map from the set of critical points of f to the set of Lie chords from L to the 0 section. So let me explain this in the baby case. So here we just have a function defined on B. And we look at the Lagrangian, which is the image of the twisted differential of f. And recall that the twisted differential of f is the map from B to the cotangent bundle of twisted cotangent bundle of B that sends a point q to the usual differential of f at q minus f of q beta of q. And now if q is a critical point of f, then the differential of f will vanish. And so we are just left with a multiple of beta. So we are in the same Lie orbit of a point of the 0 section. Okay, so we can associate to this critical point the Lie chord from the point minus f of q beta q, which is a point of L, to the point 0q, which is a point of the 0 section. So this map is injective because this Lie chord is a Lie chord in a fiber over q. So if you have a different critical point, we will be in a different fiber, so it will be a different Lie chord. But this map is not bijective because this Lie chord is a very special Lie chord. In fact, we are following the Lie flow for this time here, which is the critical value of the generating function, and it turns out to be also what we call the action of this Lie chord. So here, if we want to have a bijection, we should take, in fact, the subset of Lie chords of time shift equal to the action. Then it will be a bijection. But I don't have time to define precisely these notions, so for the purposes of the talk, it's good enough to have this injection. And then a consequence of that injection is that the first the result in the list, we always have Lie chords. Corollary existence of Lie chords from L Lagrangian Hamiltonian isotopy to the zero section to the zero section. Because we have seen that such a Lagrangian has a generating function quadratic at infinity, and then we can apply that injection. Every critical point of F gives a Lie chord. So in fact, we get that L has at least as many Lie chords as the minimal number of critical points of a function quadratic at infinity over B. So at least there's some probability numbers in the non-degenerate case, and so on. So let me now discuss translated points. So we have an SES manifold. And let me first say more precisely with an SES diffeomorphism is, so it's a diffeomorphism phi of M such that for some, so for any representative eta omega, there exists a function G which is called the conformal factor of phi, such that phi star omega is equal to Eg omega. And then a point Q of M is said to be a translated point of phi with respect to eta omega if P if the point Q and its image by phi are in the same Lie orbit, and if the conformal factor vanishes at Q. So first example, translated points of symplectomorphisms are just the fixed points. So more precisely, if we have M eta omega with the Lie form exact, okay, then we have seen eta omega is equivalent to 0 E minus mu omega, and let's call this a symplectic form omega bar. So if phi is a symplectomorphism with respect to omega bar, then the translated points of phi with respect to 0 omega bar are the fixed points. Because the conformal factor is 0 and the Lie flow is the identity. More generally, the translated points with respect to another representative, eta omega, so eta is the differential of mu, will be the leafwise intersections of phi and the Hamiltonian function e to the minus nu with respect to omega. So there will be points there such that their image by phi will be in the same orbit of this Hamiltonian, autonomous Hamiltonian. Okay, so there are leafwise intersections. So we already knew, by the way, that the translated points are a special case of leafwise intersections, so because they are leafwise intersections in the symplectization, translated points of contattomorphisms. So now we also knew that leafwise intersections are a special case of translated points, but not the translated points of contattomorphisms, but the translated points of RCS maps. Okay. And the second example is for contactomorphisms. So if we have a contactomorphism of a contact manifold Y psi contact form alpha with conformal factor G, then we can lift phi to the locally conformal symplectization by the same formula that we would use for the lift to the usual symplectization. So phi tilde over theta q is equal to theta minus g of q phi of q. So this is an LCS diffeomorphism with the same conformal factor. And the translated point, so we have that theta q is a translated point of phi tilde if and only if q is a translated point of phi with respect to alpha. And this is with respect to minus d theta alpha. So existence of translated points for contactomorphisms is a problem that has been studied by several people in the last 10 years. So now we can ask the same question also for LCS Hamiltonian diffeomorphisms. And using generating functions, we can prove that such points always exist, at least in the C0 small case. As Vincent said, it's an easy consequence of this. Well, more or less easy consequence of this result about Lie chords. So this goes as follows. If we have a phi, an Hamiltonian LCS diffeomorphism of an LCS manifold M, eta omega, then we can look at its LCS graph of phi, seen as a map from M to the so-called LCS product of M. This is a notion that has been defined by Chantraine, Sackel in 2024. And roughly speaking, it can be described as follows. So as a manifold, this is equal to the quotient of the product of the universal cover of M by the equivalence relation under which gamma 1, gamma 2 is equivalent to gamma 1 prime, gamma 2 prime, if the integral of eta along gamma 1 minus the integral of eta along gamma 1 prime is equal to the integral of eta along gamma 2 minus the integral of eta along gamma 2 prime. So if we would ask instead that both sides are equal to 0, then we would get the product of the symplectic cover with the symplectic cover. So here we are asking a bit less. We don't ask that are both 0, we just ask that they are equal, these two terms. So this LCS product is covered by the product of the symplectic cover. M bar cross M bar. It covers the LCS product. And both they cover the product of M with M, and both are covered by the product of the universal cover. And it's not difficult to show that given eta omega, we can define an LCS structure on this space so that the product of the symplectic cover is really the symplectic cover of the LCS product. And then given a phi Hamiltonian LCS diffeomorphism of M, it can be proved that there exists a unique phi bar, which is a symplectomorphism of M bar that covers phi. And then we can look at the usual graph of phi bar as a map from M bar to the symplectic product of M bar with M bar. And then one shows that this map descends to a map from M to this quotient, the LCS product. And this, by definition, is the LCS graph. And then one shows that the translated points of phi, they are in bijection with the Lie chords from the image of this LCS graph of phi to the image of the LCS graph of the identity. And using this as a corollary, we get the existence of transmitted points in the C0 small case. Of phi Hamiltonian symplectomorphism of an LCS manifold, which is a C0 small, and M is compact. Because we can use the LCS Weinstein theorem. So if phi is C0 small, then its graph will be contained in a Weinstein neighborhood of the graph of the identity. So by the Weinstein theorem, it's the same thing as being in a neighborhood of the zero section in a twisted cotangent bundle. So we can apply the previous results about the existence of Lie chords between these Lagrangians. So in the last 5 minutes, let me say something about the rigidity results we get on the locally conformal symplectization of R2n plus 1 and R2n cross S1. So in this case, we can associate a generating function to all Hamiltonian diffeomorphisms, so not just to the C0 small ones. Indeed, so this is analog, as I mentioned, this is analog to what we do in the symplectic case. It was done by Viterbo, given phi, an Hamiltonian symplectomorphism completely supported of R2n. We can look at its graph as a map from R2n to the product. R2n cross R2n. And then there is a symplectomorphism to the cotangent bundle of R2n. So we get here a Lagrangian in the cotangent bundle of R2n, but since phi is compactly supported, we can compactify it to a Lagrangian in the cotangent bundle of the sphere, S2n. So we get a generating function quadratic at infinity for phi. And using minimax on the generating function, we define spectral invariants, C plus and C minus, that have a lot of applications. So those spectral invariants, they see fixed points of phi and the symplectic action, and they are invariant by conjugation because the fixed points are invariant by conjugation. In the contact case, similarly, that was done by Bhupal. If we have a phi, a compactly supported contactomorphism, isotopy to the identity of R2n plus 1, we can look at the graph of phi as a map from R2n plus 1 to the contact product, R2n plus 1 times R2n plus 1 times R. And there is a strict contactomorphism of the contact product to the one jet of R2n plus 1. So we get a Legendrian here that can be compactified to a Legendrian in the one jet of the sphere. So again, we have a generating function, quadratic at infinity, we define spectral invariants. C plus and C minus, so now they see translated points of phi, which are not invariant by conjugation, but if they have time shift 0, then they will be fixed points. So the vanishing of C plus and C minus is invariant by conjugation, and using this, Bhupal could define a partial order. And similarly, if we have a phi compactly supported isotopy to the identity of R2n cross S1, one shows that this construction actually gives a Legendrian in the one jet of S2n cross S1. So again, we get spectral invariance, and now using periodicity of the red direction, one shows that the integer parts of the spectral invariance is invariant by conjugation, and one gets as application a bioinvariant metric, a capacity, and a proof of the squeezing and non-squeezing result in the contact case. And in the SCS case, it's exactly analog. SCS case. So now, if we have a phi, a completely supported Hamiltonian LCS map of S1 cross R2n plus 1, then we can take its LCS graph, seen as a map from S1 cross R2n plus 1 to the LCS product, S1 cross R2n plus 1, LCS product with the S1 cross R2n plus 1. And now there is a strict LCS diffeomorphism to the twisted cotangent bundle of S1 cross R2n plus 1. Indeed, so this can be done as follows. So here we have the LCS product of a conformal symplectization with a conformal symplectization. And it can be shown that it is equal to, it can be identified to the conformal symplectization of the contact product. So this is this can be identified with the conformal symplectization of the contact product. And similarly, this space, there is an easy identification with the conformal symplectization of the one jet of R2n plus 1. So we already know that there is a strict contactomorphism from the contact product to the one jet. And if we have a strict contactomorphism between two contact manifolds, we can lift it to the conformal symplectization. And so we get a map here, which is the map we want. And so here we get a Lagrangian that can be compactified to a Lagrangian in the twisted cotangent bundle of the S1, the space S1 cross R2n plus 1. It can be compactified to S1 times the sphere S2n minus 1. Then we apply the theorem of Chantrain-Murphy. We get the existence of a generating function quadratic infinity. And then exactly as in the symplectic case, we can define the spectral invariants that see translated points of phi and have exactly the same properties and application as in the contact case. And I stop here.